Hello, my name is Raymond Najjar. I'm an oceanographer at Penn State University, and I'm going to be giving you a presentation about the oceans and climate change. This presentation is for the residents at Foxdale Village, which is a retirement community in State College, Pennsylvania, where I live and where I work. And if you, those of you at Foxdale have any questions, or anyone else who happens to be watching this video have questions, please feel free to email me at the address given on this slide. If you have any comments, anything, I'd love to talk to you about this topic, which is of great interest to me. As I said, I'm an oceanographer. My particular areas of research are on the carbon cycle in the ocean. This is about how carbon moves around in the ocean, how it is transformed into different compounds, how it exchanges with the atmosphere, how it's buried, all aspects of carbon in the marine environment. And of course, that's relevant for climate because carbon dioxide is a greenhouse gas, and it turns out the ocean helps to regulate the amount of carbon dioxide in the atmosphere. The second area of research that I conduct is about the influence of the oceans on, the influence of climate on coastal areas. And a particular focus of my research is on estuaries where the rivers meet the sea. And these are very productive areas, very important. And I do research on some of that, how estuaries are changing, how they might change in the future. So this is actually, oceans and climate change is a very big topic. I'm only going to scratch the surface of it. I'm actually not going to be telling you about my particular research, which is on, a lot of it is on Chesapeake Bay, a little bit on Delaware Bay. If you're interested in any of that, again, feel free to contact me. So let's go ahead and start this topic of the oceans and climate change. I've got my outline here. So I'm going to first talk about the role that the ocean plays in the climate system. So that's just kind of how it helps to regulate mostly heat and carbon we'll talk about. And then we'll talk about the impacts of anthropogenic carbon dioxide emissions on the ocean. And that happens broadly in two ways. Carbon dioxide emitted by fossil fuel burning gets into the ocean and it affects the chemistry. Maybe you've heard about ocean acidification. That's one way in which anthropogenic CO2 emissions influence the ocean. And then the second is due to the fact that carbon dioxide is a greenhouse gas. So when it's emitted into the atmosphere by fossil fuel burning and other human activities, it warms the planet. That warming affects the ocean, and there are consequences of that warming. So we'll talk just a little bit about that. Again, it's a pretty vast area, and I'll just give a couple of examples. Then I'll discuss what we might expect in the future. And a lot of that depends on us about what what humans emit into the future. And I'll kind of lay some of that out. Talk about some of the solutions regarding climate change. This mainly is reduction of carbon dioxide emissions. This is the main solution I will focus on, how we might go about doing that. And sort of to give you some inspiration or hope that this is something we can do, I'd like to highlight some past environmental successes, some very difficult problems we've had to wrestle with and how we've come up with solutions for them. And that sort of gives me hope that we'll be able to make some significant progress with this climate problem. And then I'll talk a little bit about what you might be able to do as an individual to help us get to where we want to be. So let's talk about the ocean's role in the climate system. Broadly, the climate system is all those processes that regulate sort of the statistics of temperature, precipitation, all things weather, really. And so that involves the ocean, involves the atmosphere, involves ice, involves land. That's sort of the climate system. And the entree into the ocean's role into the climate system is really its interaction with the atmosphere. I mean, there's other ways that the ocean actually has direct impact on ice sheets as well. And so there's, all these sort of parts interact, but what I'll focus here is how the ocean exchanges heat, how it exchanges water, how it exchanges carbon dioxide, and other things with the atmosphere. So that's that's the main way the ocean plays a role in the climate system. And the focus in this presentation will be about heat and carbon dioxide. So let's discuss heat. I'm going to show you a temperature map here, and this is a little bit different than a typical temperature you might see on the Earth. It's not the temperature itself; it's the annual temperature range. So what's being plotted here is the temperature of the warmest month of the year minus the temperature of the coldest month of the year. So it's kind of an expression of how seasonal the climate is, how different the summers and winters are. And you probably know that depending on where you go, even in the United States, the range varies quite a bit. If you're over on the West Coast, as it turns out, the range is actually quite small. The summers aren't that hot, the winters aren't really that cold. But if you're here where I live in the Northeast, or if you're further north the summers can be quite warm and the winters can be quite cold. So that's a big temperature range. And you can see the red parts on this map show where the temperature range is quite large. So you see, really what you're seeing is that the range is much higher over the land than it is over the ocean. And you see that one of the biggest temperature range areas is in northeastern Russia. And so the reason why this is the case is because the ocean has an enormous heat capacity. It, when it's the sun is bearing down on us in the summertime, it's absorbed by the ocean, and that heat, because the ocean is a fluid, gets mixed down quite a bit. So the ocean doesn't warm up as much as neighboring land does. And a similar thing happens when the surfaces of the Earth are cooling during the wintertime. There's sort of heat, there's a loss of energy from the land and from the ocean, and that energy loss is kind of distributed throughout the ocean because it's mixed, and therefore the winters over the ocean aren't that severe. So the bottom line is that the ocean moderates the seasonality of the climate. It has the effect of making our summers cooler and our winters warmer. So that's reflected in this map here that shows this temperature range. So and this is in degrees centigrade. So you can see over this northeastern part of Russia, it's like 40 degrees centigrade. That's huge. That's that's like 70 degrees Fahrenheit. That's the difference in the winter and the summer. Whereas over the nearby ocean, it's only 8 or 10 degrees centigrade, maybe at most 20 degrees, 15 or 20 degrees Fahrenheit. So that's one impact on the ocean. Another is that the ocean absorbs heat from the atmosphere in tropical regions and releases it to the atmosphere in high latitude regions. And you can see that on this. It's kind of another kind of map. This is a heat flux map. The red areas are where heat is entering the ocean. And you can see that that's predominantly in tropical regions. That's probably no surprise because the sun is directly overhead in the tropics. So you get more solar radiation hitting the ocean surface in the tropics than you would at higher latitudes in polar regions. So that's the red areas, heat coming into the ocean. And the blue areas are where heat is coming out of the ocean. You can see that tends to be at high latitudes. It also tends to be kind of in the western part of ocean basins. So you can see that here's the effect of the Gulf Stream. I'll be showing you that in a minute. And there's another similar current here in the Pacific Ocean. So what the effect is of the heat being absorbed by the ocean in the tropics and released at higher latitudes, polar regions, means that the ocean currents are transporting heat from the hot areas of the planet, the tropics, to the cold areas of the planet. And so the effect is that the ocean makes the tropical regions cooler and the high latitude regions, so subpolar and polar regions, warmer than they would otherwise be, in the absence of the ocean. Turns out the atmosphere does this too. It transports heat poleward. So again, this is another moderating influence of the ocean. It's taking a place that would normally be quite warm and or in its absence would be quite warm and cooling it down and taking an area that's very cold and warming it up. And you can see the effect here maybe a little bit more viscerally in this image over the Atlantic Ocean, the western part of the Atlantic Ocean of the Gulf Stream. This is a satellite image of the sea surface temperature. And you can see the Gulf Stream here. It's this kind of meandering current. These warm colors, these reds and oranges, mean higher temperature. And this current sort of comes up the east coast of the United States, and some of this water makes its way into the North Atlantic and causes the higher latitudes to get warmer, and has a cooling effect on the lower tropical latitudes because it's carrying that warm water poleward. And you can see that in this other kind of interesting temperature map here. So this is another sort of weird temperature map, and what's being plotted here is the temperature at a given latitude, right, minus at a given location, minus the average for that latitude. So for example, just get your bearings here. Here's North America, and this is like the northern hemisphere between about 30 degrees north and the North Pole. Here's North America, here's Europe and Eurasia. This is the North Atlantic here. And you can see the North Atlantic Ocean is like 10 or 12 degrees centigrade warmer than the average for that latitude. Okay, and the reason why it's warmer is, at least in part, is due to this transport of heat by ocean currents from low latitudes to high latitudes. So so this is showing that effect, and this is why Northern Europe is relatively warm, say compared to Canada or central Canada. It's like at the same latitude as Scotland, for example, but central Canada is a lot cooler than Scotland is, and it's at least in part due to this ocean currents transporting heat poleward. So and here's a third way that the ocean affects the climate, is that it's absorbing a lot of the heat from global warming. So carbon dioxide emissions are causing carbon dioxide levels to increase in the atmosphere. Carbon dioxide is a greenhouse gas, causes the Earth to warm. And you could ask, well, where is all that additional heat from global warming going? And that's shown in this graph here. It's shown the change in the heat content of the Earth since the 1960s in these units called joules. It's a unit of energy. And the blue shading shows the heat that has gone into the ocean. And the red shows the heat that's gone into basically everything else, the land, the atmosphere, and the ice. And you can see the ocean, because it has this enormous capacity to absorb heat, largely because it's a fluid, right? And it mixes, it can mix down the heat, whereas land and ice are static. The atmosphere is a fluid too, but there's just not much of it. It's not much mass in the atmosphere. So here's yet a third way in which the ocean is kind of moderating the climate. It's absorbing all of this heat. I mean, if the ocean wasn't there, the land and the atmosphere would have gotten a lot warmer in response to increases in carbon dioxide. So again, it's a moderating influence on the climate. Okay, I'm going to continue that theme, but now we're going to talk about carbon and carbon dioxide. So this table shows the size of carbon reservoirs on the planet. So you basically take the ocean and you find out how much carbon is in it, you add it all up, and that's shown here in these funny units called gigatons of carbon. That's a billion tons of carbon. So there's carbon in the ocean, it's dissolved, that's carbon dioxide and other things. There's carbon in soils and vegetation. It's organic matter. It's like trees and soil, it's dirt. The atmosphere has carbon, it's carbon dioxide, and so forth. We have ocean sediments, permafrost. Our fossil fuel reserves is another carbon reservoir. What you see from this is that the ocean is a massive carbon reservoir. It's way bigger than everything else. And it readily exchanges with the atmosphere because it's a fluid that mixes. CO2 is dissolved in seawater and can be released from seawater. So it has a big effect on the amount of carbon dioxide in the atmosphere. You can think of the ocean as, you can think of the atmosphere as the tail of the dog, and the ocean is the body of the dog. And kind of whatever the ocean does, the atmosphere sort of follows along. So the ocean plays a big role in regulating the amount of carbon in the atmosphere. And the way this happens is, carbon dioxide is added to the atmosphere. It gets dissolved in water, and then it can react with the water to form carbonic acid, and then that carbonic acid can break up into other forms of carbon. So carbon can find its way into a whole variety of forms, and this is one of the reasons why the ocean is able to contain so much carbon, because it ultimately reacts with water. And this map here shows where the anthropogenic, that is human produced, mostly through fossil fuel burning, where that anthropogenic CO2 has gone in the ocean. Oceanographers have worked very hard at creating this sort of map. It's a complicated technique to create this map. It starts with measuring the amount of carbon that's in the water and then subtracting off what is expected there from natural processes, because carbon does exist in the ocean naturally. In fact, most of the carbon in the ocean is there naturally. And so this is kind of finding just that part that is anthropogenic. And you can see a lot of it is in the Atlantic Ocean. And that's because that current we were talking about before, the Gulf Stream moves up from the south and moves into the Atlantic, and then the water gets salty and cold enough to make it dense and sink. And when it sinks, it's carrying that carbon dioxide with it. So this is why we see so much anthropogenic CO2 in the Atlantic Ocean. And in the Southern Ocean, that's another place where there's a lot of water sinking, and so you see this accumulation also of anthropogenic CO2 in the Southern Ocean. Okay, so if we look at the carbon budget today, or at least over the past 10 years or so, this is the carbon budget for the atmosphere. We're adding CO2 to the atmosphere mostly from fossil fuel burning. There's a total of about 40 billion tons of carbon dioxide per year being added to the atmosphere. 86% of that is from fossil fuel burning, and some cement manufacturing as well. And a small fraction of it is due to deforestation, right? You cut down trees, they eventually are burned or they decompose, or the soils associated with that kind of decompose, and that releases carbon dioxide to the atmosphere. So that's the CO2 going in to the atmosphere every year. And then about a little less than half of that is accumulating in the atmosphere. And then about a quarter of what's being added is being taken up by the land, by sort of intact vegetation, and about a quarter is being taken up by the ocean by the process we talked about earlier of CO2 dissolving in the ocean and then reacting to form other forms of carbon. So this is yet another way in which the ocean moderates the climate. If the ocean wasn't there, the carbon dioxide levels would accumulate more rapidly in the atmosphere. We'd have more carbon dioxide. The planet would be getting hotter, basically. So this is an additional way in which the ocean moderates the climate. In a way, it's a good thing that the ocean is absorbing CO2 and the land as well, because that in the atmosphere it's causing heating, and that generally has a negative impact. Now, there are some negative impacts of the ocean absorbing CO2. We'll talk a little bit about that as well. That's the ocean acidification problem. So we'll discuss that in a bit. But with regard to the climate, again, the ocean has a sort of moderating influence. Okay, so that's all I want to say about the role of the ocean in the climate system. Bottom line, ocean, it makes our climate more moderate. It's a mediating effect on the climate. So now let's talk about the impacts of anthropogenic CO2 emissions on the ocean itself. So, planet's warming, and the ocean is warming. I showed you all that heat accumulation in the ocean. When you warm water, especially salt water, it will expand. All salt water actually will expand. Fresh water is a little bit different. There's a very cold water actually, when you cool it, will expand a little bit. But for salt water, whenever you warm it, it expands, and that causes the sea level to rise. So that's one way. One of the reasons why the ocean is the sea level is rising, which is shown on this graph here. And I'll talk about this graph in a second, a little bit more detail. The other way, and actually probably more important way, especially now that the ocean is sea level is rising, is because ice on land is melting. What happens to that meltwater? It goes into the ocean. So the total mass of the ocean is actually going up because of melting glaciers, melting ice sheets, particularly on Greenland and Antarctica, the warming associated with global warming and the enhanced greenhouse effect is increasing the amount of water in the ocean. So you can see that from measurements here. These measurements are blue or made from tide gauges on land. And then over the past couple of decades, we've had satellites that actually can measure the height of the sea level. They bounce radiation. They're really remarkable instruments that bounce radiation from a satellite off the sea surface and back and measure how much time it takes to get back. And of course, the ocean is higher, it takes a shorter amount of time. And as it's measuring these very small changes, and you can see that the ocean is, over the past 20 or 30 years has been rising about 3 or 4 millimeters per year. And that rate is higher than it was throughout much of the 20th century. So sea level isn't just rising, it's accelerating. And this is kind of an alarming thing that the rate of sea level rise is increasing. So the result of that is that we're getting more flooding in coastal areas, even when there's not rain, and even when there's no storm. So this so-called sunny day flooding or nuisance flooding, and here's an example of it in Miami. And this is happening all over the world. And this graphic here shows that we've had, thousands of coastal flood days in the United States since the 1950s, and about 2/3 of those are a result of the higher sea level that we've seen over the past since 1950 as a result of climate warming. So climate warming has raised sea level and has caused more frequent flooding on land. Of course, this has all kinds of negative consequences. It damages homes, damages infrastructure, damages ecosystems. And a lot of the damage that occurs whenever we have a hurricane, for example, or some kind of coastal storm, is a result of the water that is carried onto the land. And now, with the sea level higher, these storms can cause more destruction. So that's one of the impacts of a warming ocean is increased coastal flooding, and there are many impacts. I'm just giving a couple here. Another impact of a warming ocean is coral bleaching. And coral bleaching is when corals, which are symbiotic organisms, the corals are animals, but they have symbiotic algae in them, photosynthetic algae. And that's what gives the corals their remarkable color, this algae. And they bleach, that is, they lose their symbiotic algae and when they're stressed. And the stress often comes about as a result of a warming event. So here's an example of a fire coral sort of before a warming event on the left. This was in 2016, and then afterwards. Now, this doesn't kill the coral. The coral the algae could come back, but sometimes the stress is so bad that it actually does kill the coral. The algae are not able to return, or the coral is not able to accept the algae back. So this is an awful thing. And this shows some of the data behind the warming. This is showing on this horizontal axis, it's showing the amount of heating that's this particular coral reef. This is an example from the Great Barrier Reef. It's showing the amount of heating that this coral has experienced, not only in terms of the temperature increase, but how long that the warming has taken place. It's called heating weeks. And then, so that's what's on the horizontal axis. And then on the vertical axis, it's showing the percent of the reef that has been bleached. And what you can see is that the more heating you have, the more bleaching you have, right? So this is a lot of data behind this. It's not just one example here and there. It's pretty solid stuff that warming causes bleaching. And this map here shows how severe coral bleaching can be. And this is just an example from 2014 to 2017, showing the severity of the coral bleaching during this time period. And the dark the red and dark red areas are indicate a likely coral bleaching, and the really dark red areas indicate that coral mortality is high. So to me, this is one of the most troubling aspects about climate change and the ocean is the impact on corals. These are magnificent ecosystems, and they've been around for hundreds of millions of years, really. And we depend on these ecosystems for food. They play very important ecological roles in the ocean. A lot of societies depend on them, not only for food, but also for recreation. They actually serve some storm protection services. So they're really remarkable and important ecosystems. So this is a very troubling trend that we've seen regarding coral bleaching that's resulting from global warming. I'll give one other way that the ocean impacts one way that ocean warming has an effect, and that's through its impact on tropical cyclones. So you have warmer ocean, you have more evaporation from the ocean, you have more moisture in the atmosphere. That's one thing that happens. The second thing is that hurricanes themselves, tropical storms, and very severe tropical storms, which are hurricanes, sort of feed off. They're kind of heat engines, and they feed off the amount of heat that's in the ocean. And so the warmer the ocean is, the stronger hurricanes get. We may not have more of them, but it's what we've seen in the data, and what we're expecting in the future is that the strongest hurricanes are going to get stronger still. And here's an example. This is a map that just is over Texas, showing the rainfall from Hurricane Harvey a couple of years ago. And you can see this thing dumped, more than a half a meter of rain. Can you imagine 1.5 feet of rain, 1.5, 2 feet of rain being dumped on the land? And a study by Kevin Trenberth showed that Harvey, would not have produced so much rain without human-induced climate change. And that's, again, both because the warming powered the hurricane more, but also just because there's more moisture in the atmosphere. So you can create more precipitation from that. And here's another study. This is a photograph of in Puerto Rico after Hurricane Maria, and this study showed that Maria's rain magnitude was nearly 5 times more likely to occur today than in the 1950s. So, the thing is, it's not that climate change caused Maria to happen or caused any severe, Category 4, Category 5 hurricane to happen. But what it did do is it made that hurricane much worse than it would otherwise be. So that's what climate change does. It takes something bad and makes it worse. It exacerbates. It's a threat multiplier. Okay, and the other effect I want to talk about here of anthropogenic CO2 emissions on the ocean is ocean acidification. And we've talked about this reaction a little bit of carbon dioxide reacting with water. It forms this carbonic acid, and then that carbonic acid breaks up into other forms of carbon, but also you can see it makes a hydrogen ion. And that hydrogen ion that's acid, right? And that formation of that acid, that hydrogen ion, that H+, that's ocean acidification. And we have measurements of this. We've been measuring ocean acidity levels at numerous sites in the tropics and subtropics over the past 30 years or so. And we can see that the pH levels going down. And the pH, if you remember your high school chemistry, that's the negative of the log of the hydrogen ion concentration. And the main thing you need to know is that as the pH goes down, the water's getting more acidic. So that's ocean acidification sort of observed. That's ongoing. And so I'll talk a little bit about what some of those effects are. There's some experiments that have been done about that. Checking my time here. So I've got a few more things to talk about. One is future climate scenarios. So let's discuss that a bit, how things might go in the future. So there's different emission scenarios that scientists have developed and use as a way to illustrate what the future might hold for us in terms of climate. Of course, it's up to us, right? It's humans that are emitting carbon dioxide to the atmosphere through fossil fuel burning and other activities. And this shows since 1900 in black what our emissions have been. They're up to about 10 billion tons of carbon per year now, and these are some future scenarios. This red one is kind of a business as usual scenario. That is, the emissions sort of just keep going up as they have been. And then we've got one that kind of goes up a little bit, then starts to go down, and then we have one that kind of starts to go down, or right away, and we're at zero emissions, in maybe 2060 or 2070, and then actually we start removing CO2 from the atmosphere through various activities like growing trees and stuff. So let's see what impact they have. It's actually they're quite different. This is the temperature change predicted by climate models as a result of these CO2 emissions. So you can see over the next couple of decades, it doesn't really matter that much what happens. We're going to get some warming. That's maybe a little bit more for the higher emission scenario, but not a whole lot more. But then they really start to diverge as you get towards the end of this century, so that we have, with respect to temperatures around today, maybe 1 degree of warming. This is degrees Celsius here, or 1 degree of warming degrees Celsius for this low emission scenario, and like 4 times that for the high emission scenario. So, what we do in the future really has a big impact, especially as you look out towards the end of the century. And this shows the effects on sea level. And so here's how sea level has changed since 1800. You can see it's gone up. And then these are the projections into the future. There's a lot of uncertainty here. That's what's shown with the spread of these red here, anywhere between a half a meter or so of sea level rise by 2100 to, more than 2 meters of sea level rise for this high emission scenario. Whereas the low emission scenario is more like between, say, 1/3 of a meter and 2/3 of a meter. So it really does make a difference, again, particularly as you go out towards the end of the century. And these are the impacts on pH. These are averages over different parts of the ocean, and it's showing this group of curves here is for the high emission scenario. So you see, get a pretty big drop in pH. Whereas if we go with the low emission scenario, which is the dotted lines here, then pH levels kind of don't change very much. They really do level off quite a bit, and that's because the carbon dioxide levels are not changing very much. So big impact on ocean acidification in terms of the greenhouse gas emissions. It really does make a big difference in terms of ocean acidification. All right, let's talk about the ocean acidification. There's been a lot of studies that have been done on it, and this is an interesting study that recognizes that ocean acidification doesn't happen in isolation. It's happening as the climate warms. So you can't just look at the effect of acidification by itself. It really only makes sense to look at it together with temperature change. And the warming itself is going to have an impact. So what this shows here is that as you warm water, this is an example for a coral reef, and it's showing, these are experiments that were done for a coral reef, and it's measuring the calcification rate. That is how fast the coral can grow. And you can see that as you warm the water, the coral actually grows faster. That's what these two graphs, these two coral reefs show here. It's a funny graphic. And then there's another example. If you just take their coral reef and you just raise the CO2 level without changing the temperature, nothing much happens at all. But then there's this crazy thing that happens. This is kind of unexpected. When you do both at the same time, you warm and you raise the carbon dioxide level, that the growth rate of the coral actually goes down. So this is what's called a synergistic effect. The effect is not simply the sum of the individual parts. So it's typical for biology, right? It behaves in very unexpected ways. Okay, so let's talk a little bit about solutions. I only have about 5 minutes to go. Well, I think a main solution is the deployment of renewable energy. It's probably not a big surprise to you, and you can see one of the reasons is kind of an economy of scale. That as we've produced more solar panels, it's gotten cheaper to do so, and our technology has improved, and our ability to manufacture has improved. And you can see, the real precipitous drop in the cost of solar panels shown in this graph here. And now it's to the point where if you want to make an electric power plant, right, it's actually cheaper to do it based on solar and wind than it is on natural gas, even nuclear and coal. And we're not even talking about the negative impacts that coal and gas and even nuclear might have. So just from a cold-hearted, bean counting, all I care about is money point of view, we should just be building wind and solar power plants. And you can ask why we're not doing that. I think it's mostly political and reasons that's not happening. Another way we can improve or reduce greenhouse gas emissions is by considering our diet. And agriculture leads to a lot of greenhouse gas emissions, and the types of foods that you eat affects the greenhouse gas emissions. So it turns out beef, sort of per pound of protein emits there's a lot more carbon dioxide emissions than say lamb or chicken, and certainly things like soy or beans. That's it's probably an enormous amount of land that's required to raise beef, and it's also the greenhouse gas emissions associated with cattle. They release methane. So so changing your diet, moving it more towards these more sustainable forms of protein is one way. We as a society can reduce our greenhouse gas emissions. And I'm not telling you shouldn't eat beef, but maybe reducing it and considering other forms of protein, which are generally more healthy. So it has this sort of benefit, additional benefit, health benefit. So shifting to these lower emission forms has multiple benefits. And another thing that we could do is build up our sort of mass transportation infrastructure, and also make our cities more, our communities more walkable and more amenable to bicycles, for example. So, for example, if we kept our cars parked for trips less than 1 mile in the U.S., each year we'd save $900 million in fuel and maintenance costs, and we would not emit 2 million metric tons of carbon dioxide. So, and then then we get this additional benefit of being healthier as well, because certainly walking and biking has these additional health benefits. And there's a lot of these co-benefits or multi-solving associated with moving away from fossil fuels and using renewables. Another one is air quality. So burning coal and natural gas increases ozone levels, increases particulates, things that lead to asthma and other health problems. And a lot of people die each year as a result of poor air quality associated with fossil fuel burning. So that's another benefit we would get from shifting towards renewables. So what can you do? There's a lot of ways that you could participate in solutions. You could join groups that advocate for carbon reductions. One great group is called the Citizens Climate Lobby, and they have a very particular goal of getting a carbon dividend act passed. So that would basically put a price on carbon, and then the money associated with that would be distributed back to the public, and that would incentivize CO2 reductions and transition to fossil fuels. You could support international agreements like the Paris Climate Accord, right? And we have, I think we're out of it now, but with the new administration, we'll be back in it. And this is definitely a good thing, because it's the first time everyone has agreed really that we need to get our emissions down. So these supporting politicians who support these international treaties is another positive thing you can do. You can buy your own electricity from a renewable source. And in Pennsylvania, you can go to papowerswitch.com and just select your electricity from a renewable source. So if you're there at Foxdale Village, maybe you don't have control of your own electricity, but you could, and you can see if Foxdale themselves are getting their electricity from a renewable source, or you could advocate others to buy their electricity from a renewable source. Very easy. It's very competitive. The costs are very similar to getting your electricity from a non-renewable source. Demonstrations is another way. Direct action is another way to make your voice heard, and governments, companies are increasingly responding to action regarding climate change. So I'll close on past environmental successes. We often we focus on the negative often, how bad the environment is getting. And indeed, we should be worried about climate change. We still have work to do in many areas of environmental quality, but we've actually done a lot of good things, and we often forget that. So I want to just highlight a few of those. And Pennsylvania plays a role in this. We had one of the worst smog episodes in history in the 1940s in Sonora, Pennsylvania, that led to 20 deaths. And this event was really singular and led to a lot of the environmental activism of the 60s and 70s, and ultimately led to things like the Clean Air Act. And the Clean Air Act, before the Clean Air Act, this is a picture of Philadelphia here. We had very frequently these sort of smog episodes that you can see, and now it's happening a lot less frequently. Ozone levels are down, nitrogen dioxide levels are down, carbon monoxide. These are all nasty things for air quality. Sulfur dioxide, lead, all down as a result of the Clean Air Act that was passed by Congress and signed into law and its amendments signed into law by presidents, including George H.W. Bush, signed in the amendments to the Clean Air Act, which really had a very big effect on air quality. And the remarkable thing is that what this graph shows here is that our emissions have gone down as a result of these improvements, these laws, Clean Air Act and its amendments. Emissions have gone down while actually we've generated more heat and electricity. So we installed these scrubbers on power plants and things, and that really cleaned up our air. And at the same time, we actually generating more energy. And what happens to cost? It was pretty much flat. So we were able to achieve that at essentially a very little cost. And in fact, we saved a lot of money because people were getting sick less. And so we had much less in the way of healthcare costs, amounting to 170 to 430 billion dollars per year in health benefits. So it's really remarkable improvements in health and therefore in economic well-being as a result of these as a result of the Clean Air Act in the U.S. and its amendments. So it's really kind of a total win-win situation. And I think it's the same thing with climate change. It's going to be a win-win situation. Here's another example: the ozone hole, which is this loss of ozone over Antarctica. It's actually shrinking, and that's a good thing. That's what this graph is showing. The size of the hole is actually going down. That's because we passed the Montreal Protocol, right? And the Montreal Protocol reduced the amounts of the emissions of chlorofluorocarbons. So we adopted the Montreal Protocol, and soon after that, chlorofluorocarbons started slowly coming down in the atmosphere because we weren't emitting it nearly as much. And then I'll finally give I'm an oceanographer, I'll give a water quality example right near Philadelphia here. That river used to be incredibly polluted, Delaware River, incredibly polluted. The oxygen levels in the 70s were very, very low. Fish were not able to these fish migrate upstream into the watershed, and they were not able to pass by in the 70s because there's no oxygen in the water. And as a result of the Clean Water Act, we cleaned up our wastewater treatment, and the oxygen levels have kind of we're pretty close probably to what their levels should be naturally. So there's a lot of good successes out there in terms of cleaning up pretty severe environmental problems. Of course, we've got a lot of work to do on these problems that I've mentioned. Still progress needs to be made, but the climate problem we've got a long way to go. But I think we can get there, and we can be inspired by some of these past efforts. So here are my take-home messages. The first is that the ocean is a moderator of the climate system. The second is that anthropogenic CO2 emissions have negative impacts on the ocean: warming, sea level rise, and acidification. Human-induced climate change will continue to occur regardless of the emission scenario. So some adaptation is going to be required. And then the climate of the mid-century and beyond, it's very sensitive to the emission scenario. So we really need to bring down our emissions to sort of avoid the worst. And we have solutions in renewable energy. And then finally, I just want to emphasize that good science, policy, and business practices have gotten us out of environmental messes before. And that should give us some hope, that encouragement that we can solve the climate problem. So thank you very much for your time. I think I'm a little bit over the time I planned. but here are some of the references in case you want to do further reading. And thank you very much.